Well, good morning. I'll talk about Universal Chiplet Interconnect Express, UCIe, and we'll talk about what it is, what is the industry landscape. We'll talk about the interconnects in the computer landscape. We'll talk about UCIe, which is a new open standard, what does it offer, and then some future directions and conclusions. So some of the trends in the industry landscape are, we have proliferation of cloud computing, a lot of growth in the AI and analytics area, and cloudification of the network and edge. Basically, these are driving the what I call the more and more innovations, right? So that's generating more demand, which is in turn creating more innovations. And as a result, what we need is a lot of faster processing capability because of the applications that are coming up, and that in turn needs more memory capacity, more I/O bandwidth, which in turn needs more data processing. So that is the virtuous cycle of innovation in which we are in. And most of that is being driven by the data-centric revolution, and it's basically the explosion of the data, right? This is a chart from IDC that shows how the amount of data that is being generated is on an exponential trajectory. And the drivers are what we expect: cloud, 5G, lots of sensors around, automotive, IoT, you name it, right? And with these large data sets, we need to get aggressive time to insight goals. And with that, we get the scaling challenges of latency of access to the data, processing the data, the bandwidth, the capacity. So we have to move faster, we have to store more data, we have to process everything, and we need to do all of this seamlessly, efficiently, and securely. So this is the cloud computing landscape as it is today. What you see on the right is a physical structure, right? I mean, those are like huge data centers, and they're basically racks and racks or pods of servers, right? As shown on the picture on the left. And within that, if you look at the picture at the bottom, you will see that there are different types of drawers there. There is the compute drawer, memory storage drawer, and fundamentally these racks, as shown over here, they are connected through a networking kind of interface where we use copper for short distance and optical for the longer distance, and they're all connected up at the entire data center level. Now, with this structure, the key here is that the entire data center needs to be treated like a computer, and interconnects are key to driving warehouse scale efficiency in there. And today's construction of these racks are such that, or the drawers are such that there are what we call individual nodes, which is basically a server, and all the resources, whether it is the memory, whether it is your accelerators, whether it is any other kind of processing entity, belongs to that server. So those are like, at the end of the day, those become stranded resources. So the thing that the load store interconnect world is trying to address is, and they're all connected through load store interconnect, and that's because the load store interconnect fundamentally belongs to a given node. So what we are trying to do is we are trying to enable moving resources across fungibly between different entities, between different nodes. So the picture, this is my taxonomy of the classification of the different types of interconnects. For the off-package interconnect, I roughly break it into two categories, one that is latency tolerant and the other one that is latency sensitive. And we'll talk about the on-package, which also belongs to the latency sensitive category. In the latency tolerant, these are the networking interconnect or fabric, and they connect at the data center level, so naturally they are narrow but very high speed, right? And they are typically leading the all the data rate transitions. They are at the leading edge of the data rate transition, 4 to 8 lanes connected through cables, backplane. So there the key thing is to deliver a lot of bandwidth within a given small form factor, right? So that's the reason why that tends to be at the leading edge. And given that these are at the data center scale, latency is not super critical. You will see that latency tends to be high when compared to the what I would call the load store kind of interconnects. FEC latency, for example, in the networking world is 100 plus nanosecond for a transmit plus receive path, whereas in the other type of interconnect, the access latency by itself, load to use, is in that range, right? So the latency sensitive one is it's high speed, but it's wide, and what you have on the particular node level or on the particular drawer level as shown here. So these are the things like PCI Express, Compute Express Link, proprietary interconnect, like for Intel it is UPI, ultra-path interconnect, cache coherent links. These are interconnects which have got memory access semantics built into it, right? So those are load store interconnect, and they have architectural ordering semantics. They're at the node level and they're moving into the rack level. That we have talked about that with things like CXL. And currently the data rate is 32 moving to at PCIe Gen 6 speeds to 64 gig, but there are hundreds of lanes, not 4 to 8, hundreds of lanes in a given platform. So power is extremely important, cost is important, silicon area is important, backwards compatibility is important, latency is super important, and those are onboard interconnects moving onto cables and backplanes as we move from the node level or from the chassis level or the drawer level to the rack level. And there the latency is super critical. So you will see that even with PCIe Gen 6 or whether it is CXL Gen 3, we added close to 0 nanosecond of FEC overhead because we want to keep the latency to be flat. The third type of interconnect, which is the on package that I will talk about in the context of UCIe, as you can see here. So these are the different levels here. This is the part that we will talk about. These are not just latency sensitive, they're super latency sensitive. They're really wide, they are high speed, and they can be load store and proprietary. So 4 gig all the way to 32 gig, typically single-ended, NRZ, consuming very little power, very fast power transition, low power state transition, 2D interconnect, 2.5T, moving to 3D kind of interconnect on the package level. So thousands of lanes. Naturally, with that, you need to be really low power, really low latency, high bandwidth density. And we'll see that these are less than 2 nanoseconds from the PHY to the transaction layer. So fundamentally, load store with UCIe that I'm going to talk about, load store IO moves from the package level. It was there in the node level and onto the rack level. The same types of protocols span a wide range. Now, the load store interconnect, we have PCI Express, which is about 3 decades now. PCI Express by itself is 2 decades. Before that, it was PCI bus. And there the world was that you have the picture over here on the right, top right, where it basically splits the world into 2 parts. One of them is the cacheable and the other one is uncacheable. So memory that is connected to the CPU, it belongs to the cacheable kind of memory, whereas those that are connected to the I/O devices like PCI Express, those are uncacheable memory. And there are different ordering rules, but both of them are the load store semantics model, just that one is cacheable, the other one is. With Compute Express Link or CXL, which we introduced in 2019, basically we overlaid coherency and memory protocols on top of PCI Express, so the device can cache the system memory and the memory that is attached to the device can be cacheable. And it leverages the PCI Express infrastructure. And these two are very successful industry standards developed in a multi-generational way, fully backward compatible, lots of IP tools, very mature ecosystem that exists. And there is compliance program with plug and play. So with on-package interconnect that we'll talk about, what we said was that we should be leveraging that infrastructure for standardization and for load store usages, and we need to basically move seamlessly the functionality thing that exists at the board level onto the package level. So everything should move seamlessly between the node to the package to even the die level, right? Those are increased levels of integration that we go through. So the picture here represents what what we are talking about. So today's world, this is a cartoon picture where you have processors connected to memory. You got a lot of slots like these, right? And you plug in a PCI Express or a CXL card. So that's integration at the node or at the board level. With on-package interconnects, some of these components would move on to the package, and that's the package level integration. And we'll see how that's very prevalent in the industry today, except it's being done in a proprietary manner. Eventually, some of those components might get into the die for an on-die integration, but the bottom line is that you want to have the same software, the same set of IPs, and the same subsystem that moves scalably across the board to the package to the on-die level. So let's talk about UCIe, which is the topic of today. It's an open standard for chiplets, and Gordon Moore is known for his 1965 seminal paper where he predicted the Moore's law, which basically says transistors will double every 2 years, number of transistors. In the same paper, he talked about the day of reckoning, where he said that it may prove to be economical to build large systems out of small functions which are separately packaged and interconnected. Right? And we are already there today, right? If you look into the multiple product offerings, volume commercial product offerings that are being done by my company, for example, mainstream Xeon, or client products, CPU products, and if you look at other people's offering, those are all multiple dies packaged on the same package, right? And the reason behind that is few reasons, right? So one of them is, of course, as the demand that we talked about for this, for the virtuous cycle of innovation is coming through, we are seeing insatiable need for processing. And with that, we can put more and more transistors on the package. The problem is that putting them on the die is a challenge because we are hitting the reticle limit, right? There are more number of cores than we can fit on, and that's not just for us, Intel. It's true for all the companies, right? So that's a challenge that everybody faces. That you got huge amount of processing that you need to package together. Or even if you're a switch vendor, for example, you got a lot of lanes that you want to package together, and the problem is that your die size becomes bigger and bigger to the point where you're really getting reticle limited, right? So once you get reticle limited, the way you get around that is you construct smaller dies, you connect them, and off you go, right? And basically that's the technical challenge that everybody has. The other part of the challenge is with the advanced processing node, yield is a challenge, especially for larger dies, right? And the way you get around that is that if you make your dies smaller, you yield better. Now you can connect them together as long as you figure out how to connect them together, so that the basic goal is that your performance should come very close to a single monolithic die performance, right? As long as you can meet those, we are good to go. So those are the reasons why people are, pretty much the entire industry is doing, system on a chip, moving towards system on a package kind of thing. There are other usages that we are targeting, and this is represented by the picture here on the left here. So you can imagine that there is a sea of cores. You are going to have some customer IP, customized chiplets. You're going to have all of those. You're going to have some amount of memory on the package. It's a mix and match, right? It's a heterogeneous system. When you do that, it enables you to reduce the time to solution, in the sense that you don't have to put everything on the same die and have to validate that. That takes a longer time, lowers your portfolio cost, because different types of functionality might be better for different process nodes. So for example, memory typically tends to be in a different process node than logic. So this enables us to do that. Smaller die, as we talked about, yields better. It reduces the IP porting costs. The IP porting costs are going up significantly. Even if you change nothing but just port the same IP from one process node to another process node to another process node, there is a cost associated with that. Whereas if you can keep them separately on different dies and assemble them on the package, it helps with that. It lowers the product SKU cost. Most importantly, it enables us to offer bespoke solutions. And by that, what we mean is if different customers have different needs, they have different acceleration needs, so you can pick one type of an accelerator, plug in another accelerator. Somebody has needs for a lot more cores, somebody has less cores, but they need more memory. You can do all of that mix and match with, if you have a proper industry-defined standard to connect components together on the package, and that's basically what UCIe is all about. And that's the vision of UCIe. It's a mix and match of chiplets from different process nodes, from different fabs, from different companies, from different assembly houses, right? It's the same picture that we have today on the motherboard. You can build your motherboard, you can get CPUs from whoever, there are slots, you can get, you can get a NIC card, you can put 2 NIC cards, you can put 4 SSDs, right? You can get them from any vendor, plug them, it will work, right? So this is following the same model at the package level. Whatever is happening at the board level can move now into the package level if it is appropriate. And by that, what we get is, we get a lot of benefits that we will see. We get about 20x performance for 1/20th of the power, which is expected because these are much shorter channels, right? And much more lower latency. Will go through that. This shows the picture that I was referring to about the IP porting cost. This was a study done by a bunch of organizations, including IEEE, and you will see that just the process porting cost, and this breaks it down into different components, but the process porting cost is just getting increasingly higher and higher, right? So even if you did nothing and just moved the same IP across, these are the different components based on the study. So the question is, when does it make sense for us to chop a die, so to speak, right, and move them into separate chiplets and combine them, right? So on the picture, you can see that, this is a good example that, hey, a 300 millimeter square monolithic die, probably, you might want to break that up into 4 and do 75 square millimeter. And again, it's not a one size fits all kind of an analysis. Everybody has to do their own analysis, but it's basically a function of all of these, right? What's the die area, how many chiplets you can package, what's the wafer cost, what's the defect density, right? What's the strategy, and all of those things, right? And there is the product cost versus die yield curve here. So, one of them is chiplet and one of them is the monolithic. So you will see that there is the crossover point at which point you want to be basically positioned yourself. So what are the key metrics and adoption criteria for doing industry standard chiplet, right? And by the way, UCIe, we architected and specified to have the best key performance indicators, which are on the left, to the factors that affect the wide adoption. So it's 2 sets of things, right? One of them is, of course, the key performance indicators. The other one is a set of things that, encourages innovation, right, in the industry. So the key performance indicators, of course, this is, why would you do it, right? If your performance is not good, you can have all the compelling reasons it's not going to fly, right? Bandwidth density, and we give both the linear density as well as the area density. The energy efficiency in terms of picojoule per bit. So it has to be a scalable energy consumption, right? We need to be, our bandwidth, if I consume 10% of the bandwidth, I should be spending 10% of the peak power, right? It needs to scale. So not just lower power, but also scalable lower power with low idle and entry exit latencies. Latency is super critical because you're putting things on the package, things that would have been on the die, you're moving them out, right? So latency becomes super critical. Channel reach is an important factor. Reliability and availability, of course, that's very important. Cost is also important, right? So these are all our key performance indicators. On the other side, basically it's the broad thing of interoperability, right? If you're developing a chiplet, you are going to say that, hey, who do I connect to, right? You're going to say, is there a full stack? Is there a plug and play with existing software? Or do I have to go and wait for an entire software ecosystem to come and develop, right? So that's going to slow down your innovation, right? I mean, you're going to spend some money, make an investment, and you're going to look for, hey, does the standard offer me this, right? Does it satisfy different usages and segments, right? Or are you going to be a niche? There is nothing wrong in being a niche, except then you go through a different calculation, right? If it is a widely available market, that makes it easier to make an investment decision. Technology, right? What are the choices of the process nodes? Can I do it anywhere? Or am I constrained to go to a particular place? So it has to be really open from that point of view. Open packaging options. What is the power delivery and cooling solutions that I'm going to deploy? Is there a repair strategy? And this goes back to the cost aspect of it. How do I debug this? Once something is not working, right? Which basically gets to the time to market kind of thing. And then most importantly, is there a broad industry support? You can have everything else, but if hardly anybody is doing it, then I'm going to pass, right? So all of these standards that have become successful because there was broad industry support. It was an open ecosystem. So this is the learnings several of us have, over many, many decades that we have brought to bear with UCIe. So these are the components for the chiplet interoperability. We basically think of it as multiple layers, right? So one of them is, of course, the form factor. This basically talks about, what is the bump map and how do they connect to each other. Then the SoC construction issue, how do things come out of reset? How do they initialize? What is the register access? What is the security? What protocols are running on it? What kind of software interface does it have, right? And of course, the physical layer, right? All of those are important aspects, right? You can't just define a physical layer and expect that things will interoperate. So that's like me defining a SerDes and saying, hey, come plug it in the PCI slot, it will work. No, you need the other layers of the stack, right, for it to work. So for UCIe, the 1.0 specification, when we started in March, we had a 1.0 specification ready, which Intel had donated. It basically defined the physical layer. You will see the picture on the right there, shows the layering approach. So you got the physical layer, you got the die-to-die adapter, and then you got the protocol layer. The physical layer is basically the I/O part of it with industry-leading KPIs. We looked at across the industry and we put together something that was really the best in class. For a protocol, we did CXL, PCIe for near-term volume attach. The question is, why these two protocols? If you remember from the previous slide, a lot of the SoC construction issues are addressed since these are a board-to-board interface, right? People can build a PCIe device. All that they need is a clock and a reset, right? The rest of it just follows from the specification. It just comes up, right? And from a usage model point of view, with I/O attached with PCIe CXL.io, that's fairly straightforward, very well known in the industry, decades of products out there. Memory use cases with CXL.mem, and the more advanced accelerated use cases, which will need caching semantics, that we address through CXL.cache. So very well-defined specification with a compliance chapter going through how to test these things, right? Along with a lot of reliability kind of thing, if this fails, how to fail over, and then if something doesn't work, what registers to go and look at. So all of those are comprehended in the spec. There are two swim lanes for UCIe, the standard package and the advanced package. Standard package is for 2D, as shown on the picture here on the top right. You will see that you got dies, these are the bumps. Normally what happens is that from the package substrate you are going to come out in terms of package pins. Now instead of escaping there, you are going to just go and connect to another die on the same package, right? So these are cost effective and they can go longer distance. It's defined to travel up to 25 millimeter within the package. So cost effective, longer distance. Now advanced packaging on the other hand, it's power efficient and high bandwidth density. And basically for advanced packaging, these dies, they need to be placed close to each other. You'll see that there are three types of solutions that we have put here as examples, right? And it definitely works across a much broader range. The first is the silicon bridge EMIB. This is from an Intel offering, right? So you can have these dies connected through EMIB and it will work using UCIe. The next one is an interposer based one, which is CoWoS, which is from TSMC. right? As you will see, TSMC is also one of the founding promoters of this consortium. Same dies, their packaging solution, it will work. And you can get the dies from any of the foundries, and it will just work, okay? Third one is CoWoS, which is from ASE, which is one of the OSATs, right? So the dies basically can be manufactured anywhere in any foundry, any process node, assembled anywhere. You can mix 2 and 2.5D on the same package. Offers flexibility to the SoC designer, right? So you want to say, hey, I want to have this kind of acceleration functionality, who do I have? Which companies are offering that kind of solution? You can mix and match, right? Oh, I need 5 of these, I need 6 of those other type, I can package them together. I got my own bespoke solution. So, as I said, UCIe has its layering approach, so which basically makes it easy for the implementation and the evolution. Protocol layer, we map PCIe protocol and CXL protocol. So PCIe 6.0, CXL2, CXL3. If you are a PCIe from pre-6.0, there is a flit mode. So basically you leverage the CXL's .io format. So PCIe all the way through will be mapped into UCIe. Also streaming protocol. So you can come up with your own protocol and use them as raw bits, in which case you're just going to tap off here on the physical layer side, and you can do your own whatever proprietary die-to-die protocols. And die-to-die adapter is connected through a well-defined interface. So these interfaces that you see here, these are all IP to IP interfaces. So this is the micro bumps or bumps here. These are inside the die, right? So you got your RDI, which is a well-defined interface, and this is the FLIT-aware die-to-die interface. So, IP vendors will design to that, and you can make your own application layer, and you're all set to go. Yes?
Can I ask?
Yeah, sure, go ahead.
What did you say about proprietary in that? You were talking about proprietary, is it the protocol?
Yeah, proprietary protocol.
Not the physical?
No, not the physical. The physical has to be the UCIe physical, but you can run a proprietary protocol. So for example, just like we do today on our Xeons, right? You got split Xeon dies, multiple split Xeon dies, and AMD does the same kind of things, right? They have their own protocol that they run, right? So you can run that protocol on top of this UCIe PHY. So that way you don't have to do different PHYs for different usages, right? Just like PCIe, a lot of people run proprietary protocols on PCIe PHY, cache coherent protocol. That's. So the die-to-die adapter that does all the protocol parameter negotiation. It multiplexes the protocol. Fundamentally, it is responsible for the reliable data transfer. So it puts the CRC and it does the retry everything at a flit level. It also takes care of the power management, low power state, all of those things. It orchestrates that. The physical layer, of course, has got all the analog components. We have a sideband for accessing the other side, so that in case that helps with the initialization. It also helps with debug and any kind of out of band kind of access, right? So we have that explicitly defined, and then the PHY logical aspect of it. And we have a very well-defined configuration register using PCI infrastructure, so that basically is the plug and play. In fact, we have defined it in a way where even if you have shrink-wrapped OS, for example, that doesn't understand UCIe, just understands PCI, and you connect two components together. We have defined this in a way where it's going to think that it is a PCI link. Okay, so basically, it doesn't understand the other structure, which is for UCIe, which is fine. It's not going to go there. It's just going to think, oh, this looks like a PCI link. Fine. So UCIe PHY, it defines the electrical AFE for the main band, sideband. So we include everything. Actually, in this picture, if you look at any numbers we give is inclusive of these entire thing. Right? It's not just a transmit plus receive circuit number. It's the whole thing amortized, right? So we have the electrical AFE here. This is the sideband, and then this is the PHY logic, right? So basically there are 16 lanes if you are doing a standard package, 64 lanes if you are doing advanced package. There is 1 lane of valid, 1 differential pair for forwarded clock, 1 for background calibration. So that's the picture there. And on the sideband side, it's basically 2 lanes, right? 1 data, 1 clock. Clock is 800 megahertz. And it basically runs on its own separate power domain, so it's always on, all of that good stuff, right? And you can combine these multiple slices to form a larger entity. So for example, like everyone is, let's say one of the standard packages 16 lanes of data, you can put 2 standard packages together and it becomes a 32 lane link. 4 of them 64 lane link. Same way, 1, 2, and 4 you can combine. And that offers plenty of bandwidth on a per node basis. That's the point I was making here. So this is what it looks like. Your advanced package is 64 lanes of data, valid, tracking, forwarded clock, and the sideband is 4 lanes, 2 in each direction, data clock in that in and out. And standard package is 16 lanes, otherwise it's all the same. The other thing is the advanced package has got a few spare micro bumps for so that way if something goes wrong, you can substitute that and still maintain 64 lanes. And because these are bumps, just like on the external link, if something goes wrong, you just go for a narrower width. So, and we expect, because this is on package, it's to be much better than what you have for external PCI link. So this is the single cluster where you got 16 and 16. And by the way, you can construct the same thing with 64 and 64 in the advanced package, or you can have 2 of them form a by 32. In the advanced package, it will be 128 lanes. 4 of them together in a standard package becomes 64. In an advanced package becomes 256 lanes. So plenty of bandwidth. And the RAS strategy is for lane repair. You are going to do that using the advanced package. There are spare wires there, so you can substitute things that failed. Both will support lane reversal. And lane reversal is supported on the transmit side, not on both the sides, because we are being very cognizant of the latency and area. And then the width degrade, because the advanced package has got spare lanes, it doesn't need to do width degrade, but it does the standard does the width degrade. Any questions so far? So from a usage model point of view, SOC at the package level is one of the usages. So if you look at the picture here, you got a bunch of, let's say, processors, you got some accelerators, you got memory, you got a bunch of RF modem, optical and all of that. They're all connected through UCIe. And the plug and play nature of this is that, let's say in this picture, I have shown 4 dies that are processors. Let's say if you have a need that says, hey, I need less processors, more accelerators, you can then put 2 processors and then 4 accelerators. Or more memory, you can do those mix and match. And this is true across the segments, right? Handheld, client, server, all of them, they will have different needs. So just like PCIe, you are going to use them in a mix and match manner. We also have comprehended the off-package connectivity with UCIe, what we call the retimer. So think of it as, an example is co-packaged optics. So you can imagine that one of the this is the CPU package. Let's say you put a UCIe retimer and you have optical connection that goes out. It goes to, let's say, CXL switch, which in itself is constructed through 2 switch dies connected through UCIe on the same package, and then a bunch of optical retimers there. And these might be CXL or PCI links connected to pooled memory, pooled accelerator. So you can imagine that this structure exists over here. And these are the ones in each of the compute nodes. So now you can go out of each of these nodes into some other drawer in the rack and have access to a pool of memory, and that's one hop away. And it's a lot of bandwidth that you can transfer with a very low latency, right? So the ultimate vision is this, right? You want to have a bunch of compute drawers that have its own memory, it has its own limited amount of I/O, but most of your memory will be in the pool that will be spread out in different racks that you can have access to. Same way with accelerators, same way with storage. And you are going to have your own infrastructure processing unit through which you are going to connect to the network, right? And this all gets connected through a load store IO fabric, like a CXL protocol, but run over UCIe. So these are the key characteristics. So these are the numbers, right? Data rates, 4 gig through 32 gig. Fully backward compatible. If you run at, let's say, 24 gig, you have to support 4, 8, 6, 12, 16, 24. So that way you can interoperate with somebody who has designed to a maximum, let's say, 16 gig, right? These are the widths we talked about, 16 for a standard package, 64 for an advanced package. The bump pitches, of course, are larger for standard package because those are like external links. Advanced package is much smaller and going down, right? Which means that you're going to get more bandwidth density, and this is the channel reach. Now, take a look into the bandwidth density here. There are two metrics. One of them is the linear. In other words, this is gigabytes per second, not gigabits, right? Gigabytes per second per millimeter, gigabytes per second per square millimeter. So these are the numbers for standard and advanced. And these numbers are, if it is 4, you are going to get 28. If it is 32, you are going to get 224, okay? So that's the range. And these numbers on the advanced side are conservatively estimated at 45 micron bump pitch. Remember, the range is 25 to 55. 45 to 55 is the standard volume today, right? And people are rapidly moving towards the lower number. And same way with the standard package, even though it's 100 to 130, we have assumed 110 micron. And if you, for example, went for 25 micron bump pitch, then let's take a look at this number here. You're running at 32 gig. This is 1.35 terabytes per second per square millimeter, right? If you compressed it down to 25 micron, it's going to be 3.25 more than that. So you're in excess of 4 to 5 terabyte per second per square millimeter. So that's a lot of bandwidth. You won't even be able to absorb that, but the capability is there. So realistically, what will happen is once people get to those lower geometries, they're just going to run the frequency lower and save even more power, right? From a power efficiency target point of view, standard we are assuming 0.5 and advanced 0.25. Just to compare the numbers, for external interconnect like PCIe or CXL, these are roughly in the 10 kind of range, right? Some do a little better, some do a little less. 10 is a ballpark number. So we are at least, order cup 2-3 orders of magnitude better bandwidth density than what you get, which is what you would expect because these are all on the package, very tightly packed, right? So of course you should get better bandwidth density. Of course you should get better power efficiency because it's a shorter link, right? And external interconnects today have power efficiency in the 5 to 10 picojoule per bit. You're getting an order of magnitude better. Most importantly, the low power entry exit latency is extremely small, 0.5 nanoseconds, in some cases 1 nanosecond. And the spec is very prescriptive about that, right? And that contrasts to multiple microseconds of latency in the external interconnect because those are all very complex circuits that you're driving, right? These are very simple circuits. So 0.5 nanosecond is basically 1 clock cycle, right? If you're running 2 gigahertz. You can't run any faster than that to turn something on or off. So these are, and what it offers is, I can dynamically, I don't have to look for software help, right? And at the hardware level, I can just monitor what's going on in the link and just turn it off and save the power. And how much power do I save? We expect it to be 85% plus. So not quite 100% because there is still leakage going on, right? But I can clock gate everything and get 85%, which is pretty good in terms of power savings, right? And reliability, we measure that in FIT, which is the failure in time or a billion hours. And that's 10 to the power minus 10, which is practically 0. So pretty good there, right? So we talked about this, right? I mean, what are the ingredients that makes a broad interoperable chiplet ecosystem? Of course, you need to have good specs, you need to have good compliance program, you need to have broad market that with manufacturing capabilities and all of that, you need to have products to attach to, and then you need to have the tools, methodologies, IPs available. And with all of that, you are all set to run, right? And if you look into UCIe, all of those are there. We'll talk about that. So from an organizational update, we launched in 2022, March, and by June we were incorporated. And what it means is that it is a legal entity with IPR policies and all of that. There are different classes of membership: adopters, contributors, promoters. We got 6 working groups that are up and running, working on the next evolution of the technology transition. And since we incorporated, we did an election and we welcomed 2 new board members, Ali and NVIDIA. So the board members, if you look here, 10 of these were the original promoters. These are basically the leaders in semiconductors, packaging technology, IP suppliers, foundries, cloud service provider. It's effectively, it's a wide cross section, right? And the membership is 70 plus member companies at this point in UCIe, right? So off to a great start. By the way, companies have announced their IPs and validation IP availability with UCIe, which is a good sign. So that's basically where we are at. So in summary, we are up and running. Chiplets and die-to-die interface, those are essential for the compute continuum, and we deliver power efficient performance with yield optimization, all of those things. And we believe this will really propel the development of an open ecosystem. We started off with 2D, 2.5D. We'll work on 3D next. Other protocols people are planning to build on it, and so join us if you have not. And any questions? Thank you. Yes.
I'll try to keep my question short so you can repeat it. I'm still learning about this quite a bit, but I saw the word storage once on the slides. I'm having a hard time understanding the intersection between what's going on in UCIe and SNIA or storage.
Sure. So the question is, what's the relationship between UCIe? I mean, how is UCIe relevant to the storage segment of the market, right? Yeah. Anybody that's doing chips today, right? And I'll give you specific examples, right? Anybody doing chips today, UCIe is important. Without that, this is the way silicon is going to be built going forward. Let's take the example of storage, right? Even within the storage silicon, you got different components that are working. It's not a monolithic kind of set of things, right? You want to have, for example, different type of processing, maybe different type of acceleration, right? I mean, if you're doing, let's say a complicated RAID, or you're doing some kind of near memory compute, or what have you, right? You will want to have different type of, ECC mechanism and things like that, right? So you might want to think about partitioning those and have them in a separate die versus your mainstream compute. Versus, let's say, an on-fee kind of an interface, you can have that partitioned in that way, and then assemble them, right? And it gives you the flexibility at that level.
So, follow-up question.
Yeah.
What, if anything, should SNIA and UCIe be doing together?
It's a good question. So what, if anything, should UCIe and SNIA be doing together? We just started, so we are, as a UCIe, so we are multiple hats, but we are looking into where does it make sense for us to start building collaboration with other organizations. So we do, just like with CXL, we do reach out to other organizations and have memorandum of understanding, so that we are working on things collaboratively in the industry, right? We address different segments of the compute, right? Continuum, and yes, we will be looking forward to those kinds of things that going forward. Yes.
Just to clarify this currently within UCIe worlds, it's more of storage controller and interfaces, or including actual storage capacity within the chiplet?
Yeah. So the comment was in the storage world, it's about storage controllers and interfaces and storage capacity within the chiplets, right?
It was more of a question. Is it looking at both, or primarily?
It's in the early stages for me to really say anything. My guess would be it will be both of those, right? It's like if you have an interface today, right? What are you going to use it for? You can use it for anything that you really want. Again, anything that has got so for example, you can build an expander within the SoC and address the capacity challenges that you might have, right? If you look at the example I gave, like a switch, right? The CXL switch that I gave, example deliberately was that I split it into two switches and I connected through UCIe because, it might not make sense for us to build that big of a CXL switch. It becomes too big, so you might want to break it up, and it might be more economical to build it because, the volume market might want less number of ports, whereas some people would want more number of ports, and you can connect them together, right? So I would expect that from a capacity point of view, you will have similar kind of things, right? And we need to all look into those. Anything else? Okay, thank you.